stopped here and said that the correlation reduces to correlation between two frequency pulses separated by delta f reduces to this beast, right? So now if we consider this, for the correlation to be 0 or for rho, let's say ml or mn to be 0, we would want right. Agreed? Whoever is listening.
Yes, sir.
Yeah. So sync fine. So now or rather, so this sync delta ft, this has a nice property that sync k delta ft equal to 1 for k equal to 0. And so when k is 0, this will be 1. This we know. Right? And this is
Yes,
equal
sir.
to 0 when k is an integer or k is an integer or k is a non-zero integer or k not equal to 0. K contained in Z, k not equal to 0 and right?
Sir, why would it be 0 if k not equal
Yes, sir.
to k belongs to integers?
If k is Z and k is not 0, sync function. So if delta
Delta
f
f is equal to delta f
delta
is
ft
equal
is
to 1.
equal to 1, what is sync?
So won't it be
Sync.
some sync of
Then
K?
it will be 0.
So there is this delta f equal to 1 over t as well. There are two factors. What is sync of k? K. Sync of k equals 0 or 1, k equal to 0 and 0, right? For k, for an integer k, isn't it?
Yes, sir. So between what is the
Yes.
delta m, like rho m in the left side you have
Uh,
written?
Sorry?
Rho m on the left side
Yes, I
beside
have
you.
written rho mn. That is the correlation. So mn and are integers that we have said. So
Okay,
the
sir.
difference of two integers is an integer.
Okay. Huh. Yeah.
The set of integers is closed over addition. Right. So the difference of two integers is an integer. And I can write m minus n equal to k without any loss of generality.
Yes, sir.
Fine. So this. So sin k or for integer m
Sir.
and n. Just a second. Let me write this.
Okay.
rho mn equal to 0 if delta f equals 1 over t, or if the frequencies are separated by multiples of 1 over t. Yes, tell me.
Sir, like sinc of x is sin x by x, right? So
Yeah,
if it's
sine
here
of
k
pi
is
x
the
by pi x.
oh,
Sin of x equals.
okay, okay, now it makes sense. Yeah.
Makes sense. Fine. So
Yes, sir.
now if we can, we have coherent reception and we can separate out the real and the imaginary part of the signal. Then all we want is that the real part of rho mn should be 0. Right?
Yes, sir.
Then, so the real part of rho mn equals sin m minus n this times. Now this is stuck or what? Okay. Ah, this is drawing, but it's not scrolling. So how do I scroll? Let's do it this way. So, yeah, so now it's scrolling. So this you see has this complex part or is multiplied with a complex number, right? So
Yes, sir.
the real part of that would be cos pi m minus n delta f t, right?
Yes, sir.
Yes, sir.
Or this equals sin of, or rather half sin of 2 m minus n delta f t, right?
Yes, sir.
Great. So now in this case, delta f t equals,
Sir,
or
where is 2 epsilon?
sorry,
So like 2 epsilon is missing.
there's no oh yeah, e by 2.
Yes, so we don't require divide by 2 then.
So
Okay.
this,
Yes.
right?
So I think we
You
won't be requiring divide by 2.
you will
Yes,
require
sir,
divide by 2.
because sir, because then 2 sine m minus n delta ft and cos pi m minus n delta ft would get
Yeah, so
combined.
that is okay, but there's a, oh sorry, you will require multiplication by 2.
Yes, sir. So it would
Sir, a
be
multiplication will be
2. Yeah.
required.
There's a multiplication by 2
Yes, sir.
because uh, see this sin will break up into there'll be a m minus m delta ft in the denominator as well. That will have to be multiplied by 2.
Yes, sir.
Yes.
That pi 2
Yeah.
needs to be 2 pi m minus n.
Yes, yes. So it's multiplication by 2, not
Yeah.
division by 2. That was wrong. So this, so anyway, the key result is that delta ft is half, and since delta ft is half, so delta f in under coherent reception can be integer multiples of 1 upon 2t for orth. So we get the condition for orthogonality in the frequency domain. Fine.
Yes, sir.
Or you can say that so now basically what happens is that these pulses, or what you are getting in the frequency domain, is basically you are getting non-overlapping. So these are non-overlapping pulses in the right. So
Yes.
till this point, what we have done is that we have either considered pulses that are non-overlapping in time or non-overlapping in frequency. But there are tricks that we want that, or we would also want that we can have orthogonal signals that overlap in time and frequency. Fine. So consider the matrix H0 and Hn plus 1 equals Hn, Hn, Hn minus H. Now, this will produce a matrix whose columns are orthogonal to each other. Will it?
Sir,
Yeah.
for then the h1 would be basically 1 1 1 minus 1, right?
Yes.
The top
Yeah.
column. Okay.
So H1 is 1 1 1 minus 1. So the columns are orthogonal.
Yes, sir.
H2 1 1 1 minus 1 1 1 1 minus 1 1 1 1 minus 1 minus 1 minus 1 minus 1 1. Right? This is it. You can check the columns are orthogonal,
Yes, sir.
and you can extend this code a- as far as you want to. And these are called the Walsh-Hadamard matrices. And similarly, there are also something called biorthogonal signals. Biorthogonal signals that are uh, uh, um, yeah. So biorthogonal signals are signals are constructed from orthogonal signals by taking minus e for, or rather by taking the, that is, if you have m orthogonal signals that can be represented as root over e 0, 0, 0 to say m times 1. No, this is 1 times m to 0, 0, 0, 0 e. Then the set of biorthogonal signals will simply include, so these are m. The biorthogonal extension will simply include minus e 0, 0, 0, 0 to 0, 0, 0, 0, 0 minus e. All these signals.
Excuse me, sir.
Yeah, Kirti.
So, like, what is that M cross one? Like, how does the dimension of the map, this thing change? The signals.
So the dimension won't change.
What does the M cross one signifies?
So this is one. Sorry. This is 1 times m. Now is it okay?
Yes.
Yeah. I'm used to writing column vectors, but these are row vectors.
Sir, is it an extension to the original orthogonal set or is it a separate set?
So it's the see, the dimensionality of that set remains, or the dimensionality of those the space spanned by those signals remains the same.
Yes, sir.
Fine. So say suppose you have 3 orthogonal signals. This, this. Fine. So x, y. These are the 3 orthogonal signals. The biorthogonal extension would simply mean that you are considering so root e. Sorry. So if these were root over e, root over e, root over e, then these will be minus root over e, minus root over e, and minus root over e. Fine.
Yes, sir.
So this is a simple extension of orthogonal signals, and there is something called simplex signals that I should cover for completeness, though they are never used again. So yeah, let's define S dot as this and S prime M as Sm minus S dot. So the nice thing about these signals is that the distance between two simplex signals remains unchanged while the the distance between two simplex signals remains unchanged while the energy, the average energy fine.
Sir, can you repeat what a simplex signal means?
Simplex signals simply they are defined like this. So you define a simplex
SM
signal
is a weak
Sm
signal or is
prime
it
Sm minus S. Sorry, S dot. This. So the energy you can see that. So let Sm square Em for all m, or rather let Sm square be E. Fine.
Yes, sir.
Then Sm prime basically equals Sm minus. So now what you are getting is basically 1 upon m times minus, or 1 upon m times.
Sir, SM prime is the set of simplex signals.
Yes, Sm prime. No, Sm prime is a simplex signal and the set will be defined as a set of these signals.
Okay, sir. So basically, we have subtracted the sort of mean.
Yes, we
Yeah,
have
and third.
subtracted the mean out of those signals. So this reduces the energy consumption. But as such, personally or practically, I haven't seen simplex signals being used anywhere. So maybe they were invented, put into textbooks, or put to use sometime for some time ago, or a lot of time ago. But these days, I haven't seen them being used. So consequently, there is not much that I can offer you about either by orthogonal signals or simplex signals.
Sir, was there any motivation for reducing this energy like this?
See, we always want to reduce the
Reduce
energy.
the energy. Allah yaar,
Kirti?
Kitty, your microphone is on.
Yeah. Yeah.
sorry, sir.
Yes. So fine.
Yes, sir.
Yeah. Great. So now this was all about constellations and signal representation. Now So this was about signal representation. Now we'll talk about the next thing that we will talk about is signal reception, or rather what we talked about till now is that how do we encode the signals, how do we modulate them. Now we will discuss on how to get those how to get the information that we transmitted back. Fine. So we will consider the simplest case first. Obviously, we will come to more complicated cases later, but we'll consider the simplest case first. That is the or AWGN channel. You guys remember AWGN?
Yes, sir.
Yeah. So if we are transmitting signal ST receive RT equals ST plus eta t. Right? Fine.
Yes, sir.
And we had defined the notion of signal to noise ratio and perceptual quality you have done in the lab. But in case of digital communication, case of digital our task is to transmit one out of m possible signals. This is what we have done till now. We will be transmitting one out of m possible signals, and receiving that will mean that we have received the signal.
Yes, sir.
Yes. So, or what I would say that RT equals SMT plus eta t. Right?
Yes, sir.
Yes. So now we can say that signal was received correctly when are able to detect SMT, right?
Yes, sir.
Others except this
Sir,
guy.
sir, detect in the sense if we get
Yes,
the
sir.
same SMT you're saying, or does it mean like we are able to
Yes, when
classify
we
it
say
as
that
SMT?
when we are able to identify that we had sent SMT.
Okay.
Sir,
because we are
when you say
see we are sending one out of m possible. You at the receiver, you know that you are sending one out of m possible values. So you will be right when you say that I was able to, I had sent the first signal or the fifth signal or the 18th signal, and you detect that properly, you'll be right.
Yeah, sir.
Yeah. So uh, uh, that we we will be able to say that we received correctly when we transmit, when we are able to detect the right signal, or from the received signal we try to estimate what was sent and get m hat. So the message here is actually m, what signal was sent, or the index, right?
Yeah.
Uh, can you say that slightly louder?
Yes, sir. Fine.
Yeah, so the message here is m. So we want to recover m hat and get m hat, that
But
is,
the message is SMT, right? Oh, you have coded the M into SMT.
yes, yes,
Okay, sir.
fine. So that is what was, so basically, if you remember, are essentially transmitting ST from the signal constellation S that contains, so this is S, yeah, and S is S1T to SMT.
sir,
Yeah,
sir, but this looks like we are trying to estimate the signal from the current uh, received signal only.
yeah.
Then
Right now I'm talking about transmitting.
okay,
Okay, so we are transmitting one out of these signals.
yes, sir.
That's what we are doing. And therefore, if we are transmitting, so RT, so let's say transmitted SMT. Let's say we transmitted SMT. Then RT will be SMT plus eta t, right?
Yes, sir.
And now want to make sense of RT at the receiver.
Yes, sir.
So in order to make sense of RT at the receiver, and
So,
we know,
Sir,
so what is meant by sense of RT?
means uh, suppose I send you a text message, you will read it
Yes,
and you will try to, by reading it, you will try to understand what is written in that text message.
yes.
You will try to make sense of it.
Okay, okay.
And suppose this, see, this received signal is corrupted by noise.
Yes.
So talking practically, if I say that I so let me you guys can access the chat box.
Yes, sir.
Yeah, so yeah. So did you get something in the chat box?
Yes, sir.
Can you make sense of it? Is this correct? Or
Mm,
is this what I wanted to send?
it's understandable, but not correct completely.
Yes. You can make sense of it, but it's corrupted by noise.
Yes.
You have to make sense of it. But to understand it, you have to make sense of it. Right?
Yes, sir.
Now, when you receive this via you have a dictionary with you. You have a vocabulary,
Yes, sir.
and you match it to what you are basically doing is you are you when you look at this word, you see that it doesn't match with what you know.
Hmm.
So
True.
you try to look around and try to guess. Okay, there's nothing that matches my vocabulary here, but it's something close to what matches my vocabulary.
Okay. I am
So
predicting.
you are the receiver. You are trying to make sense out of a damaged signal,
Hmm.
right? Obviously,
Yes,
I
sir.
missed a few letters in understand, but again, you know that under STD is no word. So you look around and try to make sense of it. Similarly, when a received signal is corrupted by noise, so basically what happens is that suppose I transmit from VPSK and with -1 and 1. Fine, we transmit minus and 1 and 1 and suppose a lossless channel. Assume a lossless channel. So someone is
Sir, lossless and noiseless are same things.
no,
Or
no. Lossless means when I send one, I receive one plus some noise.
okay.
Losses we will talk about later. Fine, but just assume that SM is once you S can be either 1 or -1. Fine. So you can send either this or this VPSK or
Yes.
rather binary PAM, whatever you want to call it.
Yeah, both are
Fine.
same.
Both are same, but yes. Now suppose pick one, -1 or 1. Choose one.
One.
Okay, 1. So this is 1. Fine. So this is I transmit this. Now because of this, noise gets added because
Yes.
there is noise. So noise will get added.
Yes, sir.
Random noise, additive white Gaussian noise. That can land you here. Oh, that can land you here. That can land you here. May land you here as well. It depends on the noise variance.
Yes, sir.
Can land you here. Can land you here. You might even end up here or here, depending on the noise
Yes.
variance.
Yes, sir.
Yes, sir.
So based on what you receive, you will try to guess what was sent.
Yes, sir.
Agreed.
Yes, sir.
So you will receive, you might receive one of these points and you will try to guess what was sent. So what we have is that we want, or we now want to make an guess. Not a guess, an intelligent guess. For making a guess, you can, for all purposes, make the KFC old guy sit there and blurt out numbers. But that won't work. So what's the name of that KFC guy? Anyone? I don't remember it.
So you're speaking about the KFC owner.
The guy whose photos picture is there on KFC.
Colonel Sanders, sir.
Yeah, Colonel Sanders. So for all it is worth, if you want to make a guess, you can make Colonel Sanders sit there and blurt out numbers. That won't help. So you want to make an informed guess or an intelligent guess based on what you have received, or your guess should be based on what you have received. Or so for this, we will derive, or we will look at what is known as an optimal for these signals. And so before we start with this model, we want to, or so this is the simplest, or this is the simplest channel model, but it gives us an basic idea of what to expect, and it isolates the effect of noise and other elements can be added on. Fine. So now we get RT equals ST plus eta t, right? So do you see a problem here?
The eta.
No, eta is a problem, yes. Other than eta, so when whatever we have done till now, or whatever signals we have understood that for we have understood those for vector signals as vectors, but this is a signal as a signal, or this is a waveform. So the first thing that we would want to do here after receiving RT vector receiving RT is to the right.
So then you have to introduce the orthonormal vectors, right, in order to
Yes,
fix it to
yes,
single space.
yes. So we will do that.
Okay.
That is precisely what we are going to do. So I receive ST. So ST, or rather I receive RT. Now RT equals SM, or rather SK. What did we use? Did we use phi or did we use psi?
Sir, 5.
My laptop battery is dying. Just a minute. Let me put in the charger. So we use phi. So this is SK phi phi kt plus eta t. K goes from 1 to n dimensions. Fine.
Yes, sir.
Yeah. So now we want to get a vector R that can help us right. Agreed.
Yes, sir.
So if we have ST equals summation K equal to 1 to n SK phi kt, then how do I get SKs?
Sir, just like optimal weights.
Yes. So basically SK equals sorry. Right.
Yes, sir.
Yes, sir.
So also if ST and phi t are known to be finite time signals existing in the range T1 to T2, say let this be closed, or yeah, existing in the over existing over the time t1 to t2. If this is true, then what happens?
Integration between
So that
T1 to
integral
T2.
becomes finite.
Yes, sk equals t1 to t2 st dt dt, right? Or
Phi k star. So
oh yeah, phi k star, sorry. Or st, this is st, and let's make it slightly bigger. Yes. Rather, this is incorrect. This is wrong. So let's cross this out, and I'll draw this again. Same thing, just that I, instead of treating those as filters, let me treat those as multipliers. Phi 1t conjugate, phi 2 conjugate t, phi n conjugate t. Fine. And followed by t1 to t2 dt. Finite time integrator is easy.
Yes, sir.
Fine. And so
Sir,
here
but
you can get,
simple,
yeah.
sir, simple multiplication would be hard, right? Mm, like,
You okay? So okay, you haven't. So you have done AM
yeah.
in the previous. So what is that?
Okay, so we'll
How
use the
is
same.
simple AM done? Achieved.
Okay.
This is nothing but pure AM multiplication, right?
Yes, sir. Yes, sir.
So fine, you multiply it like this, and this is called the correlation receiver. And what happens? So if I feed, so this is how I extract the symbols, or this is how I will extract the components when there is no noise. So what happens when I apply this RT to a correlation receiver? So the question is, what happens when apply T? Yeah. So should we answer that now or tomorrow?
Sir, tomorrow.
Okay, great. So we'll answer this question tomorrow. Okay then. Bye. Have a nice day.
Thank you, sir. Bye.
Thank you, sir.
Thank you, sir.